All right. So today we're going to study next big topic in control theory, namely observers. We're now going pretty fast into all kinds of new territories. So let me just remind you what we have done in the last two lectures. In one lecture, we covered discrete systems. So we added to the whole realm of continuous differential equations with which we were able to work. Another realm of discrete equations, like difference equations, if you want to call them that, discrete dynamics. And we were able to extend quite a lot of our methods and ideas into that direction, right? Then one last lecture, we managed to find what is optimal control. So best possible control for a given cost function. We limited ourselves to quadratic cost function. That is why we got linear quadratic regulator out of it. It is the best possible control for a given cost function. Alternative to pole placement, very useful tool, right? So now we are branching yet another direction. And all of this, I want to point out, is possible because we got the background from the first part of the course. Right? So now that we understand stability, we understand why we need stability, we understand the difference between stability and input response. Now we can sort of build on that and expand relatively fast in our knowledge. So today we're going to have yet another expansion, cover yet another big and interesting topic. Right. So I would motivate it by explaining, the problem first. So let us look at our familiar, system of equations: x dot equals to ax plus bu, right? And as we usually do, we control it using feedback. U equals to kx. By the way, notice that we could put minus here to have a more traditional minus kx, but we don't have to. If we don't put a minus there, the minus will be inside k for the stability. So don't be thrown away by appearance or disappearance of the minus sign in front of k. It's you can do it either way. So anyway, our familiar x dot equals to ax plus bu, and u equals to kx, right? Now we want to do it in practice. We want to do this control system in a practical reality, in the lab. You want to go downstairs into the underground lab. You want to implement a control like that for a real robot. Now, what you will quickly find out is that to implement this control, what you need is not only k, right? We learned how to do k twice already, right? We learned pole placement in the practical sessions, and we learned LQR last lecture. So we know how to find k. We know what criteria to use, etc. But we also need to know x, right? There are two components. One is k, another one is x. In the equations, there is no question how to find x. X is just a variable. We simply say kx equals to u, no problem. But in real life, when you're going to code this in your control loop, like you run a loop infinitely where you calculate u, apply it to your robot, calculate u, apply it to your robot. How are you going to get this x? Where is it going to come from? Now, in practice, the way you find it is if you are going to use this type of control, you're going to use estimation of x rather than x itself. And the estimation of the x will be based on measurements. All right. So that's what's going to happen. You're going to estimate x based on measurements. Okay. let's look into it a little bit more. So why can't you have X directly? Like, why not design a robot in such a way that X will be available to you, right? Let's say we are talking about a KUKA robot. Why not directly measure the whole state? So each joint position, each joint velocity. Let's say we have a drone, like a quadrotor. Why not measure position, uh, orientation, velocity, angular velocity? Why not? Well, first reason, and I think the most common reason that you would see in simple practical examples is lack of sensors. So often enough, you simply don't have a sensor to measure something. So often enough, it is difficult to expect to find a sensor which would measure a certain component of your state. All right. So often enough, it is difficult to find a sensor. For example, if you have a flying robot, to measure your height, what kind of sensor will you use? You could use a air pressure sensor, which would estimate the height based on air pressure. You can use a distance sensor that points down, which would measure the height directly using some optical trick. Obviously, air pressure does not drop so precisely that you can actually get good precision. Distance sensor only works on a very small distances. So even if you can do it, it will be pretty weak, right? But at least you can do something. But what about your position, for example? What about your position, XY coordinates of your robot? How are you going to get those? You can say, oh, we can get them from GPS sensor. Good, if you have GPS, good for you. But what if you don't have a GPS? What if your robot does photography inside a structure, like indoors photography? You don't have a GPS indoors. And mobile robots indoors are not a crazy concept. So often enough, you might not have a measurement of a particular value. And in practice, there are plenty of values which you don't measure directly. So it's not very surprising, right? So lack of sensors is a typical issue. Another one is your measurements are digital, right? So for example, they're done in discrete time intervals. So it means that your measurements are not available all the time. They're only available in updates. Like every so many milliseconds, you get a new update. They are also obviously quantized. So you don't have a measurement with infinite accuracy. Your measurement can go from one quantum to another quantum, like from, let's say, if it is encoded as a binary, let's say, is encoded as 1 bit, it can go from like 128 to 129, something like this, but cannot go like in between those, right? So there is a finite accuracy because of digital measurements, right? That is much less of a issue for very well designed robots, but it is quite typically an issue for hobbyist robots. So for robots that, for example, you build for a quick experiment in the lab, right? That can be an issue. If for example, if your encoders are not very good, if your rate of update for your sensors is not very good. Sometimes the type of sensors cannot update very fast, like the sensors are slow themselves. So it can cause problems in practice. Now, another one is disruption of measurements. So let's say for some reason you cannot perform a measurement. It can happen, especially if you have measurements that are somehow interacting with outside world, right? So for example, for your position, you rely on some kind of base station or indoors GPS or actual GPS, but there is a cloud in the sky and you are like way up north where your GPS signal is not very good. It depends, right? But what I'm trying to say is sometimes you simply cannot get a measurement for a short period of time. So like on average, you have this measurement, but right now you don't. Already you don't have an x. And notice, if you're going to do u equals to kx control, you have to have x. Like you cannot just decide, okay, right now we cannot do anything, but in 5 minutes we'll be back. You have to control all the time. Like if you have a flying robot will just fall to the ground and it's not going to get up if you don't provide it with control. Your cooker arm may run into a wall or whatever if you don't provide it with control. Like you have to give it control all the time, right? Okay. Now, another one is unmodeled kinematics or dynamics, right? Now, what do I mean by that? Well, for example, your links in your robot can bend slightly. Even for precise robot arm, there is a slight bend in the links. For hobbyist robots, like for example, let's say you're building like exoskeleton, a very thin links with a lot of leeway in joints and everything, there's going to be a lot of bending going on in that robot. Right? Also, gearbox backlash, that is standard for a lot of robots. If you're having a gearbox and your robot is not using extremely precise, very expensive motors, it's very typical that you would have slight like dead zone backlash, etc. What I'm talking about is your motor stands, but your output shaft can move slightly, like a degree, half a degree. That's enough for there to be a difference between what you're measuring on the output shaft and what actually happens on the input shaft, for example, or what you're measuring on the input shaft and the link that is attached to the output shaft. Like there will be disconnect is what I'm trying to say. Also, there could be friction. So sometimes you would expect, like a direct connection between force applied here and the effect produced there, but there isn't because there's dry friction. All kinds of things like that can happen. So at the end of the day, because of this unmodeled dynamics, the robot can behave so much more complexly than your model of the robot that even the definition of what state of the robot means can start to become suspect. Like if your robot essentially have a serious like difference between how your input shaft of your motor, inner shaft of your motor, and the output shaft on which the link is attached behave, if they behave significantly differently, you can start thinking about those two as two different degrees of freedom. You may stop thinking about it as like 1 degree of freedom associated with a joint. You may start to think that the motor has 1 degree of freedom, the link has another degree of freedom. And it could be much more complicated than that. So often enough, for some robots, the problem isn't even like the sensors. The problem is that the dynamics is very complicated and it somehow is not appropriate to just assume that your relatively precise measurements reflect the actual state of the robot the way you define it, right? They can be performance like that. Also, your sensors themselves, they can be imprecise. So a lot of cheaper sensors or simpler sensors would not be precise. For example, pressure sensors can be like those very simple ones, very small ones. They can be relatively imprecise. And the reason isn't that you cannot buy expensive sensors, but because you don't want to install very big, reliable sensors and you want something cheaper and smaller, sometimes. Some sensors, such as the LiDAR or GPS sensors, they're just naturally imprecise. They naturally produce errors. Sometimes sensors are non-linear, so they would behave linearly on certain range of measurements, but then they would have a non-linear part of their range. So, and sometimes the sensors are linear as long as temperature is correct. But change temperature significantly, and they will start to behave slightly differently. All kinds of things happen. So while it is possible to control for all of this, in some cases you have to deal with those kind of things. And they can be biased. Of course, if your sensor is simply biased, as in it measures always 1 degree more than expected, you have to recalibrate, right? Though sometimes, it's not like very typical, but sometimes maybe you would acquire a bias during a long operation, for whatever reason. It could be simply like mechanically the sensor moved slightly because it was installed incorrectly. So there are reasons. And even if you, even if you do all of this perfectly, like you don't have any of this, there would still be physics which would prevent perfect measurements. Some kind of physical effect would always prevent you from getting exact information. So you cannot rely on having X with infinite precision. Now, before we move on, I just want to say that this is a very serious topic for people who do practical, industrial, commercial robotics. So for all of those, there will be very serious and very carefully thought out solutions. So for example, if you're going to work with the robot arm, people who design robot arm would consider all those questions like, bending links and gear backlash. All of this would be considered. Some of it, like maybe gear backlash, would be avoided by having extremely precise mechanism. Links, bending, so this would be taken into account when you describe the workload of the robot, etc. There will be a lot of very careful consideration of at which frequency your sensors operate, and often the frequency will be gigantic. It will be completely out of your need, like it would be so high, the update frequency, that you cannot have problems from that, and so on and so forth. Like in practical robotics, people often try to solve those. So I don't want to give you attitude that the world is wild and we need to come there like into a jungle with like a backpack and try to solve everything ad hoc because nothing works. No, in practical robotics, often enough, things work, and people who design the robots come up with very specific solutions which are suitable for a particular robot. That is not the ticket for you to not worry about those things, because that is only true for specific commercial robots which are for which those solutions were possible. Rather, it is a reminder for you that sometimes it is a person who designs the robot who take care of a lot of this. Like you don't always have to do it. So just so you don't get a message that everything is terrible in practical robotics. But I hope I convinced you that this is something to worry about. All right. Now, how do we solve this from the linear control perspective? So we are not going to discuss here how we design robots to avoid those problems. We're going to consider how linear control can address this kind of issues. Now, the way we do it is like this. We consider our standard robot. Here it is. X dot equals to AX plus BU, Y equals to CX. That's our plant, our LTI system with the state matrix, control matrix. In this case, C is observation matrix, so measurement matrix. We consider that Y is available to us directly from sensors, for example. Right. So that is our standard LTI. To the standard LTI, we add additional differential equation, which we describe like this. X hat dot. So X hat is estimate of X. So let's say X hat dot equals to some kind of observer, which is a function of X hat, U, and Y. Right? We'll go back into it in a second. But before we go, let me look at the last one. U is equal to minus K X hat. Okay. U is equal to minus K X hat. Now, let us study what is different between this proposition and the previous one. First of all, in our control law, we are not going to use x, which might not be available to us. Instead, we are going to use x hat. X hat is an estimate of x. And while estimate of x can be wrong, it can be imprecise, all kinds of things are possible about it, but it is always available. So one good thing about it, it is always available because it is a variable stored in the memory of your computer. So estimate of x is simply your best guess what x is right now. Okay. Now, that's how we are going to do it in this lecture. There are other ways to do it. That's not the only way to deal with this problem, but that is a popular way to deal with this problem. Now, so first key observation is u is going to be equal to minus k x hat, not minus kx. Now let's make second observation. Our observer is some kind of differential equation which uses as an input y, which is always available. We assume that y is our measurements. The fact that they're always available is not like necessary for you know, how should I put it? There would be ways to avoid having like requiring y to always be available in case you are worried about like sensor disruptions or like if measurements are not available at some point. It will be possible to deal with this situation. But for mathematical simplicity for this class would require that y is always available. So x, we don't know. So we simply don't know. But y, we always know. So that is the assumption here. That is why we can, our observer, this mechanism that would estimate for us x. Observer takes y as input. It is a measurement, right? U is always available. U is just comes from here. So we know what control is. And x hat is our, you can say current value of estimation. So if you look at it carefully, what happens here is your observer somehow updates your estimation, right? So here is a rate of change of your estimation, and that is produced by the observer. And to produce this rate of change, it uses current value of estimated x, control, and measurements. That will be the idea, right? That will be the idea. Now, in terms of notation, we would make sure to differentiate between actual state and actual output, x and y, and estimated state and estimated output, x hat, y hat. Now, estimated state, x hat, I think you already understand. It's what we are going to use in all of those equations, right? That is our best guess what x is. Now, estimated output is not, I think, as clear. So let me try to make sure that you understand what I mean. So estimated output is simply x hat multiplied by c. So it comes from this equation, right? So a real output is c times x. Estimated output is c times x hat. So y hat is equal to c times x hat. The idea is that if we have this estimation equation, right, here, we can predict what kind of output we should have been seeing, right? And that you're doing by multiplying your estimate of x by c. Since this equation, we know that how it works, right? We know that c times x is y. We don't know what x is, but we have the estimate of x. So if we multiply by c the estimate of x, we should have correct y if our estimate was correct. If it is not correct, it will be something different. So estimate of y is simply a way to compare what we guessed with what we should have guessed, right? We don't have access to x, so we cannot compare x with x hat. But we have access to y, and we have access to y hat, so we can compare those. That is important distinction here. All right, good. By the way, if there are any questions, please tell me. No? All right. Now we will have to use some kind of estimation error metric, right? Because if we're going to estimate something correctly, we need to discuss the error of the estimation. So we can define difference between x hat and x as epsilon. We want epsilon to go to 0. The only problem is epsilon is impossible to compute because we don't know x. Like in practice, we cannot compute it. We can discuss it in formulas, but in practice, we cannot compute it. So that is why we introduce another error that is output error. Output error. So those types of errors we will describe as y tilde. So notice this small tilde here. This y tilde, that is how we're describing difference between y hat and y. So those are standard notations. In a lot of papers and textbooks, you would find hat describing estimate and tilde error. Now, we're assuming that this is always available for us to compute. So that is something you can actually use. All right, good. Now, let us look one more time at our favorite LTI system, state space. So we want to estimate x as x hat, and we want to do it as well as we can. We can make a proposition. What if x hat should behave the same way as x does? So x hat is equal to a x hat plus x hat dot, sorry, is equal to a x hat plus bu. So we just take this equation, but adapt it to x hat. So basically we're saying, like, since we are estimating x, why not pretend why not run the same dynamics as robot runs in physical world, but on the computer, right? We'll just simulate it forward and we would predict what x is. Now, if this equation was describing the real robot correctly, which is our assumption, right? And if we knew initial conditions perfectly, and of course, we are also assuming that the measurements here are perfect, like y is actually equal to cx, right? Sorry, in this case, we don't even need this assumption, right? We don't even need this assumption. So as long as we know initial conditions, and as long as we, our dynamics equation is correct, well, we could actually do it. Like this equation 6, it would actually predict x hat perfectly. Because they are indeed the same equations. So as long as initial conditions are the same, you would have exact same behavior. But of course, you don't know initial conditions. That's the point. Like you're not going to know initial conditions. So it would have been cool. You won't need measurements, but it's impossible. Initial conditions are not known. That is the whole thing for almost anything. It's a very standard problem. All right, but it was a good attempt. Now, we could incorporate our information about the like measurement information in the same way like we incorporate control. So the way we do it is, if linear control was minus kx, right? Why not make why not make correction law for observer to be minus L y tilde? So notice it is the same as kx, but instead of x we have y tilde, so error, our output error. L would be a gain, controller gain, but now for observer, not for controller, for observer, right? And remember that this guy, y tilde, is equal to c x hat minus y. So what we have is our LTI from the previous slide, x hat dot equals to ax hat plus bu. And to it, we add this L, right, times y tilde. Notice that this minus sign leads to those changing, switching around. So this minus sign makes y and c switch signs. So that's the idea. Now this idea has a name. It is called Luenberger observer. It's called Luenberger observer. Okay. So Luenberger observer, the idea of it is that you imitate your dynamics. So your observer in structure imitates the dynamics. Plus you have this feedback observer gain. That is the idea of Luenberger observer. Now we're done, except we don't know what the gain is. So the only problem is we need to find what L is, right? So like this guy, L. Before we find it, we cannot apply it in practice. But if we find it, we can. All right, let's try to find it. So there is a standard way to work with those things. I'm showing you it right now on the slide. So I will go through it, but please take note that what I'm showing to you is basically like a standard sequence of steps to prove stuff and derive stuff when it has to do with Luenberger observer. So it is useful to know because like in practice, you probably need to at least like somehow interact with this observer if you are working in the field. So maybe you would derive your own version of the observer. Maybe you would work with Kalman filter or something else. It's good to know the sequence of steps. So the first step is we get our original dynamics and we subtract it from observer. I mean, left and the right hand side are equal for both equations. So if we subtract them one from another, the equality still holds. This would produce observer error dynamics, right? So if we subtract them, that is what we have on the left-hand side. Right? Let me do some color coding, okay? So this is on the left-hand side, right? On the right-hand side, we have this guy from here, this guy from here, and we have, let me do different color coding. And we have this guy from here, right, with a minus sign. Notice that this guy would cancel this guy. So typically on this first step, when we discuss the error dynamics of an observer, we would be able to cancel control because it is not needed for observer dynamics. Somehow the error of the observer does not depend on the control, so it would cancel. next, what we do is we collect, we take A out of the brackets. So this becomes this. Right? And also we notice that y is equal to cx. And we can, again, switch around those by putting minus sign outside. Here is the only reason I didn't put minus sign outside is because I think that is what you see in textbooks, this form. Right? Okay, so we put minus sign outside. And next, what we'll be able to do is to also put c out of the brackets here, right? So we again would have x hat minus x, x hat minus x. And remember, x hat minus x, we define it as epsilon. Epsilon. So what happens next is, let me be careful again. This becomes epsilon from here. This becomes epsilon from here. So you have A minus LC times epsilon. And of course, this guy becomes epsilon dot. Right? Just in case this, it feels strange for you that I didn't define epsilon dot and I already use it, just write this as d dt of x hat minus d dt of x. And then remember that differentiation is a linear operation, so you can take it out of the brackets. Yeah. All right, good. So equation 10 gives us aerodynamics of the observer. Let us use it. So this guy would be stable, and notice it is autonomous LTI, so we can discuss stability here. It is stable as long as this matrix is Hurwitz. So this matrix has strictly non-positive eigenvalues, real parts of the eigenvalues, right? And it will be asymptotically, that would be marginal stability if it has this, or if it is, they are strictly negative real parts of eigenvalues, it is asymptotically stable, right? So essentially, we just need to find such L that makes this matrix Hurwitz, that makes this matrix stable. And let us remember how we usually do it. Usually we have A minus BK, and we know how to make it Hurwitz. We just do pole placement on K, and that's it. Like, just run pole placement on it. Or we can run LQR on it, right? Now, the difference between that and this, sorry, and this is the location of the gain. So the gain is located before the C matrix. In our control example, K is located after the B matrix. But here the gain is located before C. So we cannot just use the same algorithms as before and run, find gain, because the location is wrong. Okay. So we cannot do observer design using LQR or pole placement in this form. We have to do something. Okay, that's important detail. Important detail. To do something, we observe interesting mathematical fact. If this matrix is Hurwitz, then transpose of this matrix is also Hurwitz. So eigenvalues of a matrix are equal to the eigenvalues of the transpose of a matrix. All right, that is interesting property. I'm not sure, does it feel obvious to you that eigenvalues of a matrix are the same as eigenvalues of the transpose of a matrix? Is it obvious or is it not obvious? How do you feel about it?
I think yes, because it's not affects the calculation of determinant. So
So somehow what you're saying is you know that determinant of a transpose is the same as determinant of a additional matrix. And because
yep,
of
and
that,
we use it to calculate eigenvalues, so it's the same.
it's a very good intuition. Of course, to me personally, this would require additional proofs that determinant of a transpose is the same as determinant of the additional matrix. But that is not very difficult to prove, right? It's relatively simple. It's very good. It's very good. I think also if you do eigendecomposition of a matrix and you transpose the eigendecomposition, you'll be able to see that the structure of what you get as a result would still be eigendecomposition of a different matrix, and should be possible to prove from that eigenvalues are the same. But at the end of the slides, I have a formal proof. So I think, yeah, I think there will be at the end of the slides there will be proof. So in case you want to prove for this fact, it will be at the end of the slides in the appendix. Now, this fact gives us power to do the following. Instead of trying to find such L that this expression is Hurwitz, we find such L that this expression is Hurwitz. We just transposed. Notice this is the same as control design now, because control gain appears on the right of the matrix. So there's A minus BK, A transpose minus C transpose, L transpose. So this whole thing behaves the same as control gain. So instead, we don't need to do anything else. We just now plug it into our previous formulas. So for example, if we want to do LQR, we find L transpose by doing LQR for A transpose as a state matrix, C transpose as a control matrix, and choosing Q and R. If we're going to do pole placement, we would have done also A transpose would have been a state matrix, C transpose would have been a control matrix, and poles would have been eigenvalues. So notice we don't need to do to learn new techniques to get this gain. Old techniques are sufficient, and we don't need to prove. Go through LQR one more time, like LQR for observers, because this is sufficient. This is sufficient. That's very good. And those Q and R will determine aggressiveness or sensitivity of your observer. So if you can ask it to try to observe very closely, but at the cost of changing rapidly your estimation if new data is available, which sometimes is not good. Or you can ask it to be more gentle, so it will be slower to change, less ripples, less oscillations, less reaction to bad inputs, for example. Okay, all right. So that's how you tune your game. So I think with this, you can see how the whole thing is done. So here is, let me put it in a box. Here is the final result. Our original dynamics, our observer, our measurements, our controller. Any questions about that? Now, I have a question about that. Would this be stable? Notice that it is a autonomous LTI. It's not obvious, but you can see that Y and U, they look like external inputs, but they depend on the state. So you can substitute them and you would get an equation which is just depends on the state. So it is autonomous LTI. So I can ask a question of stability. So is it stable? Can someone make a judgment about that? Is it going to be stable or not? Those matrices are stable. Would this equation 12 be stable? No takers. No one wants to make a guess. All right. So we will try to prove that it is stable. But I want to point out that you cannot just assume that it is stable. And the reason is not just pedantic. I mean, after all, at the end of the class, I'm going to prove that it is stable. The reason is not pedantic. It's not just to show that I can prove it mathematically, instead of just trusting your correct intuition. That's not the case. The reason is because in the realm of observers, there are many observers that look very similar to Luenberger, which you cannot assume that they are stable. Like this. Notice what we did. We designed stable controller. We designed stable observer. But we did not say anything about combined effect of those two. Together, they may make the system stable. They may make it unstable. What I'm going to prove in this lecture is that it is always going to be stable for Luenberger observer. So the way we did things in this lecture, I'm going to prove that they will always result in a stable system. But there will be different observers, slight variations in how they behave, for which you wouldn't be able to make such a judgment. You won't be able to design a stable observer, design a stable controller, and hope that together they form a stable system. The system might become unstable. So the way I'm going to prove it is important, partly just to understand how those things come about, how my, this confidence in stability comes about, but partly to understand if you have a slightly different observer, how do you judge if it can be tuned like we did here, separately from controller? So you need this information to be able to work in practice with those things. Now, this system, after substituting, instead of y, we substitute cx, right? It is here. Instead of u, we substitute minus k x hat. And we get this equation 13, which is a LTI, autonomous. So it depends only on the state, no external inputs. Now, we can also write this in this form, right? We can write it as a state space equation with a block matrix. How we did it? We introduce this vector x hat. To get x dot, you need to multiply x by a, right? So like this. You need to multiply minus bk by x hat, so minus bk. To get x hat dot, you need to multiply lc by x, right? So lc goes here. And then you need to multiply a plus minus bk minus lc by x hat. So that's how you get this, right? Oh, 14 I turned into 15 this way. Now our next order of business would be to make a change of variables to make it simpler, because right now it is difficult to work with. So the first change of variables that I'm going to introduce is this: e equals to x minus x hat. Yeah. This looks strange because we already have epsilon, which is, as far as I remember, x hat minus x. But here, this minus sign just makes it slightly easier, so that's why I'm doing it. But also just good to know that you can do it. You can introduce those variables, different ways. Like you don't need to sort of try to memorize the signs, where to put minus, where not to put minus. Those things are not something you need to memorize ever. You need rather you make a decision how you define your variable, and then you go with it. If your decision was wrong, you change the sign and go again. So don't try to memorize where to put minus, where not to put minus. That doesn't help. Just try to understand the process, and then if your decision was suboptimal, change the sign. Okay, from this, it follows that x hat is equal to x minus e, right? So x hat, you put it to the left-hand side, e to the right-hand side, you get this. Now, how do we use it? Well, first of all, e dot, let me try to be careful. E dot is equal to x minus x hat, right? So it is x dot, right, here, minus x hat dot here. Let us now simplify. We notice that this guy, I'll try to be careful. This guy will cancel with this guy. This minus, 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 so the plus, so they cancel. This guy, sorry, what else cancels? This guy, x minus x hat, is e, right? So we get e here. And we have here a x minus a x hat. X minus x hat is also e. So we get e dot equals to a x minus x hat minus lc x minus x hat, which is a minus lc e, right? So we were able to write another type of aerodynamics. And the result is a minus lc times e. All right. Now, what we want is to take this equation and get rid of x hat here. So x hat, remember, is equal to x minus e. So we put it into here. Okay, into here. And what's going to happen is you would have the same, let me use different color, would have the same ax minus bkx, right, from here. So minus bkx plus bke, so plus bke. So that's what happens with this equation. So we have two equations. One is equation for the state, one equation for the error. By the way, very typical for this for observer design, or like for a lot of those things. Like error equation, state equation. It's very typical. Okay. Now we have two equations, and here they are: state equation, error equation. In the matrix form, it looks like this, and a minus bk times x plus bk times e, and e dot is equal to 0 times x, a minus lc times e. Okay, so this is what we got. Now, another piece of linear algebra. For block upper triangular matrices, the eigenvalue of the block upper triangular matrix are eigenvalues of the blocks on the diagonal. So for this matrix, the eigenvalues of the whole matrix are eigenvalues of the block A minus BK and A minus LC. That is a piece of mathematics. I also prove it in the appendix. I'm not going to do it now. By the way, for anyone, is this intuitive, or this is not intuitive anymore? I guess not intuitive anymore, right? Okay. Okay. Yeah. So the proof in the appendix. Yeah, but that's how it is. That's how it works. So what we have is the proof that for the closed loop system, and all of those, that's a closed loop system. So after we substitute our observer, we have eigenvalues, which are eigenvalues of the closed loop system with the controller, closed loop system with the observer. So A minus BK, A minus LC. And those are stable because that's how we just designed a controller and observer. So notice, we don't need to design them separate together. We can design them separately. And together the system will be stable as long as they separately are stable. Now, this is called separation principle. For Luenberger observer, if the controller and observer are stable independently, the system overall is stable too. That is a very unique result, and it holds for a few types of observers, but not for all of them. So there will be plenty of observers for which this does not hold. So if you're going to apply this sometimes, you have to make sure that it holds. You cannot just assume that it holds. For Luenberger, it does. For linear system, it does. But there's so much more than just linear systems, right? What is also interesting is I did all of this for continuous time. And I think if you try to do the same for discrete time, you more or less find the same exact derivation. Right? It's not going to be much more difficult because notice if you always replace x dot with like x sub I plus 1, how different are the equations going to be? Not much different. So we don't need to do a lot of extra work for discrete systems. Separation principle and all of that, you can already use it. Of course, for your own peace of mind, it's good to rederive all of this for discrete systems. And if you are thinking about it, it's a great exercise. That's a great exercise to try. If you can rederive all of this for discrete systems, probably you understand the entire lecture. Yeah, but yeah, should be straightforward. Right. That was a little bit fast, I think. Let me double check with you. I think we are like we still have something like 25 minutes, no? 20?
25, yeah.
25 minutes, okay. Well, I'm not going to keep you for 25 minutes. My apologies, we went through the lecture fast. So just for your sort of like entertainment for 10 minutes, if you will allow me, I'll show you the appendix for this lecture. Sometimes we don't have time, but today we have. So let's spend 10 minutes understanding the mathematics behind it. Yeah. Here's a simple one. I think that's the one you said that you understand already. So it's quite clear. What do I prove here? Given matrix M and its eigenvalue and eigenvector, we can prove that the same eigenvalue would be is the matrix M transpose would have the same eigenvalue, right? So the technique that I use here is just write mv equals to lambda v, because of this expression 19, I can write expression 20, put them on the left-hand side, it's equal to 0. That means the matrix is degenerate, so determinant should be equal to 0, right? And here, what I use is, as I think it's exactly what you suggested, right? You said that the determinant of a transpose is the same as the determinant of a matrix. So I take transpose of this matrix. It looks like this. Determinant should also be 0. And from this, it follows that there exists some kind of vector u, for which n transpose times u is equal to lambda u. All right. Good. Exactly what but it was impressive. To be honest, I'm impressed that you were able to give me the gist of this proof, like in a second. That's impressive. That's good. Now for the second one. We used this fact that for the block upper triangular matrix, the eigenvalues of A and C will be eigenvalues of M, right? So M eigenvalues of M, it's eigenvalues of A and eigenvalues of C. Now let lambda and V be an eigenvalue, an eigenvector of A, and mu and U be an eigenvalue and eigenvector of C. Now, first we prove that lambda and this vector V and 0 are eigenvalue and vector of M. How do we do it? Or we just multiply this matrix by this vector, like this, right? It will be A, let me do this. Like this times this is A times V, B times 0 is 0, 0 times V is 0, C times 0 is 0, so 0. And what we got is A times V, but V is eigenvector of A, so A times V by definition is lambda times V. So we proved that, and like this proves that lambda is eigenvalue of the vector matrix M. Right? So very direct. Now for the second one, we can prove that mu is eigenvalue of M, right? So here we just assume that mu is not an eigenvalue of A. So it's like standard case where we ignore the repeated eigenvalue issues. Repeat eigenvalue always create more interesting, more complicated mathematics. So in this course, I always stay away from them. But in all proofs, there would be possibility to do repeated eigenvalue cases. Just the mathematics is going to be a little bit more longer. All right. So eigenvector in this case is this complicated beast. Right. So as before, we just multiply our matrix by this vector, right? And yeah. So what we okay. When we multiply them, what happens is this guy times this guy going to be here, right? Now this guy times this guy is going to be here. And finally, this times this is going to be here. Okay. Next is one of the standard tricks where you, like in this case, I think it is, let me just be careful. Yeah, in this case, what we do is we replace this identity with I minus A times I minus A inverse, right? So we have identity here. We can easily replace it with matrix times its own inverse. And since inverse exists, right? This inverse exists because mu is not eigenvalue of A. Right? So since this inverse exists, so we can replace I with I mu minus A times I mu minus A inverse. So I mu minus A and I mu minus A inverse we take out of the brackets. Here it is, right? And this A remains in the brackets here. Okay, that's what we did. And the downstairs C times U is by definition equal to mu times U because mu is eigenvalue of C. All right. Sorry, U is eigenvector of C. Now, this clearly cancels with this, so it goes away. And what we are going to have is this expression here, which is just mu times this inverse here times BU and mu here. Mu we can take out of the brackets, we get mu, and what is left is exactly the same as this guy. This and this is exactly the same. That's the proof. That's the proof. You can see that the proof is not crazy, but it requires a little bit of ingenuity with coming up with this guy. But it's not crazy, and that's like part of, I guess, my overall message for this course. Almost all the proofs that we have seen so far are not very difficult, right? Like the most complicated things that we saw was like how to solve ODE forward, maybe how to derive Riccati equations from Hamilton-Jacobi-Bellman. Maybe when we substituted sine omega t into LTI to find Bode expression for state space system. But they're not very complicated. As in, we don't do anything that requires like some level of analysis that is you're uncomfortable with. All of this is basic linear algebra, a little bit of calculus. Same with those proofs, like those, they are also relatively simple. And I think it's good to treat them as such. Like they're simple, so you can always rederive them, you can always check them, you can always double check. Instead of trusting what the textbooks say, you can just double check, derive by yourself, make sure that it works for you. I think this attitude helps you to build like confidence about what actually goes on there. And also it helps you with your intuition. So my recommendation for everything, like you would think that this has definitely nothing to do with control, right? It's block diagonal matrices. But by understanding a little bit better how, those small mathematical components of control work, you would understand better how control in general works. Like, for example, this already tells you how eigenvectors would relate to each other in this block diagonal matrix. The theorem was about eigenvalues, but the proof gives you eigenvectors. So, something you get for free. Right. I think that's it. I would stop the recording, and if you have questions, I'll be happy to answer.